go. All right, this is Buoyancy and the Propagation of Error by Derek Lin and Daniel Liu. So there are definitions for this unit that you'll need to know. The first one is absolute uncertainty, and this represents the margin of uncertainty associated with the measurement. The second definition is relative uncertainty, and this compares the size of the absolute uncertainty with the size of its associated measurement. The third definition is systematic error, and this is error that arises from the flaw in equipment or design of an experiment. This means that this error could be replicated if you have the same exact design of an experiment with the same exact flaws. The fourth and final definition is random error, which is error that arises from uncontrolled or uncontrollable variables in an experiment or measurement. And this means that this cannot be replicated as easily. So there are also some formulas that you'll need to know in this unit. The first one is uncertainty in addition and subtraction. This is E4 is equal to square root of E1 squared plus E2 squared plus E3 squared, where E1, E2, and E3 represent the experimental uncertainties given in the form N in parentheses plus minus EX. The second formula you'll need to know is uncertainty in multiplication and division. This is percent E4 is equal to square root of percent E1 squared plus percent E2 squared plus percent E3 squared. And in this formula, percent E1, percent E2, and percent E3 represent the uncertainties converted into percent relative uncertainties. The third equation is relative uncertainty. There's actually two equations, relative uncertainty and percent relative uncertainty. Relative uncertainty is absolute uncertainty divided by the magnitude of measurement, and percent relative uncertainty is just 100 times relative uncertainty. So in relative uncertainty, the measurements are in the form of n plus e, where n is the magnitude of measurement and e is the absolute uncertainty. And it's important to note that relative uncertainty should be a dimensionless quotient. So the last formula that we'll need to know is the buoyancy formula. This is used to find true mass of an object that is being weighed. So in this formula, we see there are multiple variables. So m is the first variable, and that's the variable that represents the true mass of the object that was weighed. M prime represents the mass of an object measured with a balance. dA represents the density of air, and that is 0.0012 grams per milliliter. dW represents the density of the calibration weights, which is 8.0 grams per milliliter. And finally, D represents the density of the object that was weighed.
So now we are going to do some practice problems. The first part of the problem is to find the formula mass of potassium chloride along with this uncertainty. The information needed for this problem is uncertainty formula for subtraction and addition. So the first steps that we need to do is to write the atomic masses of each element along with this uncertainty. These uncertainties can be found on the periodic table on the front cover of the textbook. This number will then need to be divided by radical 3 to get the absolute uncertainty. These are the atomic masses of each element with its absolute uncertainty. Using these absolute uncertainties, we can plug these numbers into the uncertainty formula for subtraction and addition to get the absolute uncertainty for the final answer. After doing that, we get that the absolute uncertainty is 0.001. After doing this, we find the atomic mass of the compound, which is 74.5513. We need to remember the real significant figure rule, which is that the decimal place of the first non-zero number of the absolute uncertainty is the decimal place of the last digit of the final answer. After all that, we get the final formula mass is 74.551 plus or minus 0.001. So now we are going to do the second part of the problem. A student prepares a solution of potassium chloride by weighing 5.782 plus or minus 0.003 grams and dissolves it in a volumetric flask with a volume of 500 plus or minus 0.07 milliliters. Find the molarity of the solution along with its uncertainty. The information needed to solve this problem is the uncertainty formula for multiplication and division. We also need to know that relative uncertainty equals absolute uncertainty divided by size of associate measurement. We also need to know that percent relative uncertainty equals relative uncertainty times 100. Then we convert all the absolute uncertainties given into percent relative uncertainties. After converting it to percent relative uncertainty, we can find the percent relative uncertainty of the final answer, and we get 0.054%. Then we find the molarity of the solution by using molarity equals moles over liters, and we get that the molarity is 0.153062169. Then using that relative uncertainty equals absolute uncertainty divided by size of associated measurement and percent relative uncertainty equals relative uncertainty times 100, we can find the absolute uncertainty for the final answer, which is 0.00008 or 8 times 10 to the negative 5. Then using the real significant figure rule, we can get that the final molarity is 0.153062 plus minus 8 times 10 to the negative 5 molar. Now moving on to the third part of the problem. Ignoring the uncertainty, what is the true mass of the potassium chloride with a density of 1.93 grams per centimeter cubed that the student used to make the solution at 25 degrees Celsius? For this problem, we're going to need to use the buoyancy formula that was shown before, and it's shown here right now. M equals M prime times 1 minus density of air divided by density of calibrated weights, all divided by 1 minus density of air divided by the density of the object being measured. We know that the perceived mass on the scale is 5.782 grams, and the density of air at 25 degrees Celsius is 0.0012 grams per milliliter. The density of calibrated weights is 8.0 grams per milliliter. And as said in the problem, the density of the compound being measured is 1.93 divided by 1.93 grams over a centimeter cube. After knowing all this information and plugging into the formula, we get that the true mass of the potassium chloride is 5.785 grams.
And that's a wrap on our presentation. Thank you so much for watching.